Hi, and welcome back to Unit 5.1. This is part 3. Again, we're focusing on the first half of key question 1, which is quantifying chemical equilibrium. Okay, so you've already practiced writing equilibrium expressions, but there's something that we kind of need to know about equilibrium constants is that they're all quantified in the same way. They're all products of reactants, but sometimes they're not necessarily measuring the same things. For example, you could measure molarity, which is the ones we've seen, or you can measure pressure, um, or you can be given a K of a very specific system, and that will tell you the reaction that corresponds to it. So let's just look at the different types of K. You actually have seen this before in Unit 2, so this may be somewhat of a review. Starting off with different amounts. All you've looked at so far are equilibriums measured when the amounts are measured in concentration. And that sort of makes sense because there's only two phases of products and reactants we can use here, aqueous and gas. And you can measure the concentration of an aqueous solution, of course, but you can also measure it of a gas. So this one's pretty simple. The other thing, since we're dealing with gases, we can measure the amount of a gas through its pressure. And so the other K that we could use is called Kp or K pressure or whatever. And this one you can only use for gases. So if you had an aqueous substance in there and you were looking at the Kp, just note that whatever that aqueous substance is, you can't measure the pressure of that aqueous substance does not correspond to this amount. So that's not going to work. So, but if you have a system where there's just gases in there, this is perfect. All right, let's talk about specific systems here. The other thing is if, let's say, for example, you have an acid or a base, we can use Ka and Kb. And again, that's going to tell you something about the reaction because Ka corresponds to the dissolution or the ionization of an acid, and Kb corresponds to the dissolution or ionization of a base. And so that you will see later on in this unit, and you have already seen it in Unit 2. All right, and the final one you also seen in Unit 2 is the KSP, which this one's for salt. So this is kind of pretty easy here. All of these systems have to do with ionization, dissolution, or dissolving an acid, base, or salt. And then the little subscript here, A, B, SP, kind of tells you what it corresponds to. So A for acid, B for base, and SP for solubility product of a salt. All right, let's go back to the KC versus KP. So you've have seen how to do KC. Well, what does KP look like? KP pretty much looks the same as KC, except for the amounts are in pressure. So again, it's products of reactants. So instead of saying the concentration of D raised to the power of D, it's going to be the pressure of D raised to the power of D, the pressure of E raised to the power of E, all divided by the reactants, which are the pressure of A raised to the power of A and pressure of B raised to the power of B. So it's pretty much straightforward, the same thing, except for no longer concentration. We're dealing with the pressures now. All right, let's say, for example, for some odd reason, you have the KC and you're like, hey, I actually want to know the KP, or vice versa. Is there a way to go from KC to KP or vice versa? There is. There is this handy dandy equation, which is shown here. So it says the KP is going to equal to the KC, so the K when you're at concentration, times RT to the power of delta N. So what are the R and the T, etc.? So R is the gas constant, and that should make sense because we're dealing with gases here. T is the temperature in Kelvin, and N is the change in moles of gas. So that's super important. Basically, it's the moles of product that are in a gas form minus the moles of reactants in the gas form. So you can't, let's say you have a liquid or aqueous or whatever, you can't include that in terms of the change in the moles. Just anything that's in a gas you can include. All right, let's try the CFU. This is pretty much a straight chug and plug sort of thing. So you have this equation, this is the equation that you're going to use, and I'm asking you to use the information found in CFU2 to calculate the Kp for the synthesis of N2O4. So here's a quick hint about what exactly do I mean. If you recall from CFU2, way back in video 2, I believe it was, you had to calculate the Kc in that CFU. So that you just go back, flip in your notes, figure out the value that you got there for the Kc for the synthesis of N2O4. The gas constant is a constant, and that's the value of it. So you just plug that in. The temperature is actually written on that table in CFU2. So if you go back, you'll see that it tells you the temperature. It says 100 degrees Celsius. You have to convert that to Kelvin, of course. And then delta N is the change in the moles of gas using the balance equation. So this is the balance equation here. Again, it's the moles of products of gas minus the moles of reactants of gas. All right, so pause the video now, try the CFU out, and when you press play again, the answer will be revealed. Okay, so here's my work for the KP. This is the KC value. They were roughly around 4.7 no matter what experiment you use. This is the value of R, and this is the temperature in Kelvin. The change in moles of gas is 1 because we start off with negative 1. That's important. Sign is important here. We start with 1 mole of product and minus 2 moles of reactant. So 1 minus 2 gives you negative 1. And that's the value I get for KP. So that means that the KC is 4.7, but the KP is 0.15. If you're not 100% sure how this is done or what this looks like, I've linked this video here, and you can watch the video anywhere from 0 to 8 minutes and 39 seconds. In that video, it shows you examples. So if you just want to see like the mechanics of how to solve this, that video could be helpful. Okay, so next CFU here, I want you to actually prove prove that this equation works by using your PV equals nRT equation and molarity equals moles of solute over liters of solution. And of course, your algebra skill. Basically, you're going to derive this equation. Now, what I suggest for you to do that is I suggest you start with like KC and write KC as concentration of products over concentration of reactants, and see how you can convert the concentration of products to pressure of products and concentration of reactants to pressure of reactants, and see if you can do that. So this is actually a really super important skill for any scientist because we utilize math to sort of derive a lot of equations, and this is also an AP level skill. So this may be tested in various ways on the AP exam. So pause the video now, see if you can derive this equation, and when you press play again, the answer will be revealed. Great. So here's the simple answer to that. The answer is you're going to watch the video, the same video that you watched before. It's from 8:39 to the end. She quickly shows you how you sort of can derive it. And that's super cool because a lot of times scientists don't want to memorize things, and the way that we avoid memorizing things is just knowing some fundamentals, like knowing the PV equals nRT equation and molarity equals moles of solute over liter solution, and knowing that K is always product of reactants. And then from there, we can figure out other things. So that's why doing this sort of thing is important, is because memorization is not an effective way of learning for many things. All right, so you have gone through 5.1. I would take a moment to sort of reflect and sort of summarize what you've learned, any questions that you have, so you can come in next week ready to tackle problems, AP level problems. All right, that's it for this video. Have a quality day.